field at the center of a circular coil.
At the center of semicircular coil or circular coil? Okay, so this was a topic. Nafisa?
Yes,
This
so
was a topic.
semicircle.
Yes, sir.
Semicircle. Semicircle. So means this thing we have completed. So here the important things are the two formulas we will have. I have written the formula here for the semicircle, for the arc, and these things. So I have I told you modified right hand thumb rule? Means curl your finger along the sense of current. The direction of the thumb will give you the
No, so
direction
you
of.
haven't told.
Not told. So how? I have told you because without this derivation will be incomplete. So I'm telling it again. Okay. So if suppose this is your wire, this PQ is your wire, na? And you want to find the magnet direction, only direction I am talking about. I want to find the direction of the magnetic field at the center of the coil, at the center of the this type of wire. Okay. Semicircular, arc, or circular wire. So suppose this is your wire and you want to find the direction of magnetic field at this point. So what you will do, just do it by yourself. Curl your finger along the sense of current. Curl your finger. This current is anti-clockwise or anti-clock. This current is in this direction. So just curl your finger along the direction. See where your thumb is going. Away from you or towards you. Matthew. The direction.
Inwards, out.
Inwards.
Out,
Inwards
out.
means away from you. Something is going away from you. Away from you means going towards your screen, means going into your screen. Into your screen means inwards. And inwards is also known as negative z-axis. All these points you should know clearly. We will use all these points in the numerical. Otherwise, you will not get the numerical. Okay. So now I think we should solve some numerical on this. And for solving the numerical, first read the numerical properly, okay, and just learn the only important formulas. Not all the formulas I am saying. There are requirements of important formulas only. And okay. So this is your question now. This is your question. Hey, this is a wire like this. First, this is the straight, and then it is semicircle, and then a straight. So this whole thing is a wire. So you have to find the magnetic field at the center of semicircle. Means here at this point O, you will find the magnetic field due to this combination of wires. So what I am doing, I am just dividing this wire into three parts. Okay, so first part is this. This straight wire is the first part. This semicircular wire is the second part, and again this straight wire is the third part. So we will have to find the magnetic field at this point O. So what first we will find. Hello Nawal, how are you? So Nawal, we are discussing this question. Okay. We are discussing this question, and in this question, we have to find the magnetic field at this point. Okay. And there are different types of wires here. Means combination of different types of wire. So I have just divided this combination of wire into three wires. So first, what I will do, first I will calculate the magnetic field due to this wire at this point, then magnetic field due to this wire at this point, and then magnetic field due to this wire at this point, and add the magnetic field vectorically, because magnetic field is a vector quantity. So I will do this thing. And in exam also you should solve this question like this. And for the direction we will use the right hand thumb rule. Okay. So uh, uh, for the total magnetic field at this point O, what I will do, I can write this as V1 means magnetic field due to the wire 1, and V2 plus V3. This is finished. Now we will calculate the magnetic field due to this wire. So can anyone tell me what will be the value of magnetic field at this point O due to this wire 1? Nafisa, this is the straight wire and this is a point along the length of the wire. I think you have forgot the things. See this point. Whenever the point where you will you have to find the magnetic field is lying along the length of the wire. At that point, due to the wire, the magnetic field is 0. See this. So in this question, the magnetic field due to the wire 1 and the wire 3 equal to 0. So V1 and V3 is equal to 0. V1 is equal to V3 is equal to 0. Now for the semicircular wire, we have this formula. What is the formula for the semicircular wire? Mu naught I divided by, can anyone tell me?
Pi r the k cap.
Yeah, this is the formula. So these are the three formula that you have to learn. For the R, you will you have mu naught I alpha divided by 4R, and for the circular wire, you have mu naught I divided by 2R. But for the semicircular wire, we have mu naught I divided by 4R. So here is the circular wire, the semicircular wire. So B2, we will use this formula, mu naught I divided by 4 into R, and R I am supposing the radius. A is the radius of this semicircle. So when you will apply this, mu naught is constant and I is the current flowing here. Here in this wire, the current I is flowing throughout the wire. And 4 instead of R, we will put A. 4A. So now for the direction, we will apply modified right hand thumb rule, and you will get the direction inwards. Inwards means negative z axis, and the unit vector you will use for the negative z axis is minus k cap. Okay, is minus k cap you will use. So for making the this v2 as a vector, you will multiply this with minus k cap, and when you will put this v1, v2, v3 in v0 in this equation number 1, so finally you will get your answer v0, v1 is 0, plus you will put v2 mu naught I divided by 4a minus k cap and plus 0. So your final answer will be mu naught I divided by 4a, and this is minus. So this is your final answer. Just put it down. And remember, at least these three formulas plus one Biot-Savart law, two Biot-Savart law formula, one vector form and scalar form. Okay, just note this down. When completed, please ask me to scroll down. I think Nafisa has completed. Nafisa completed?
No, sir, I'm still drawing the diagram.
Okay, no problem. I know that your writing is very fast, so that is why I say completed. Nawal completed.
Yes.
Just complete this. You have to just remember the formulas and you'll apply the formula and direction you can get from the right hand thumb rule, whether the simple right hand thumb rule or the modified right hand thumb rule. So don't confuse why I have written here the minus k cap. Minus k cap represents the inward direction. And today we will discuss one very important derivation. It is magnetic field on the axis of circular coil.
Yes, sir, finish.
Matthew, done?
1 second. Done, sir.
So next is this question we will discuss. I will discuss these two questions. So I am taking this question first. So this is the question now you have, and in both the these both are circular coils or circular wires. In both the wires, the magnitude of the current is same, but direction of the current is different. Okay, you can see in this diagram. And suppose this bigger coil, I am supposing it as 1, and this smaller coil is 2, coil number 2. So the radius of this smaller coil is A, and the radius of this bigger coil is small b. So, and you have to find the magnetic field at this point O. So what you will do simply again, you will just write magnetic field at this point O is equal to V1 plus V2. V1 plus V2 you will write. Then now we will calculate V1 here directly. So what will be the formula? Mu naught I divided by 2R, oh sorry, 4R. This is the formula for the circular coil. Mu naught I by 4R. If you don't know, you can check here. So mu naught I divided by 4R. Sorry, mu naught I divided by 2R for the circle. So minus 2R. And this is for the coil number 1. This is for the coil number 1, this coil. Now see this coil. So just apply the apply your modified right hand thumb rule. When you will apply, you will curl your finger, and your thumb will be away from you, means the negative z axis. Here you will multiply with minus k cap, and instead of this r you will put a. Okay, instead of this r you will put not a, B you will put, because we are calculating for the coil number 1. So this is 2A. And for the, now see this smaller coil, you will apply the formula mu naught, current is same, and 2B you will use, sorry what I wrote, just a minute, just remove all these things. See now again, coil number first, we will use the formula for the magnetic field mu naught I divided by 2R. This formula we will use. Okay. So when you will apply this formula for this coil, so you will write mu naught I will be the current 2, and what is the radius of this first coil, bigger coil B. Here you will write B, and for the direction you will use minus K cap. And for the second coil, when you will apply, you will write mu naught into I divided by 2. What is the radius of the second coil? This is your second coil, that is A. Okay. A. And for the direction, just apply the modified right hand thumb rule. So your thumb will be towards you, means positive z axis. So you will multiply this with plus K cap. So finally, you can take common mu naught I divided by 2. Mu 0 I divided by 2, you will have here minus 1 by B of K cap plus 1 by A of K cap. So you can write this mu naught I divided by 2. So when you will do the calculation, you will get 1 by A minus 1 by B, and this will be K cap. This is your final answer. So these types of question you will get, and you will solve these questions like this. Now, if you have any doubt, then please ask me. I don't think you should have doubt. So you can copy this question and answer also. When completed, ask me to scroll down.
Can you scroll down, sir?
Nafisa, scroll down.
Yes, sir. Yes, sir. Scroll down.
Are you getting the motion of my cursor? Means, are you getting the motion of my cursor? Matthew?
Yes,
Not
sir.
with. Okay. So copy this and we will solve the next question.
Yes, sir. Finish.
Matthew has finished.
1 second. Yeah, done, sir.
Nawal is taking a screenshot. Uh, Nawal completed.
Yes, sir.
So means you the motive of solve this question is make you understand. It's, you should understand this, na? You have to just apply the formula and direction. For the direction, you will apply modified right hand thumb rule. Now I am taking another question. This question we will solve. So this question is same as that of the question we have done earlier, but this time the plane of the coil has been changed. Okay. So your coil number one, you can see here. Yeah. For your coil number one, the plane, your coil number one is placed in XY plane. Okay. XY plane is the plane of your screen or plane of your copy. And coil number second is placed in YZ plane. What is the YZ plane? YZ plane again and again I have told you. YZ plane is if some suppose this is the your XY plane and suppose the coil is placed like this. This is your y-axis and this is your x-axis, or your coil is placed like this. So this coil is placed in YZ plane. So, and one thing also you should know, if your plane of coil is XY, then definitely your direction of magnetic field will be x-axis, along x-axis. And if your coil in YZ plane, then definitely the direction of your magnetic field will be uh, x-axis. If your coil is in XY plane, then your direction of magnetic field will be in Z-axis. Negative or positive you will get by applying the modified right hand thumb rule. And if your coil is in YZ plane, then your direction of magnetic field will be along the x-axis. Okay, YZ and x-axis. So two coils are given. So you have to find the magnetic field at this point. Again, you will apply the same formula. V naught is equal to V1 plus V2. And for coil number one, same formula you will use. For the coil number one, you will use mu naught I divided by 2R. Okay. So you will write mu naught. This time the current is I1 in this coil, I1. You will write current I1, mu naught I1 divided by 2. And the radius of both the coils here is R. Radius of both the coils is R. So over here you will write 2R. Now for the direction you will apply, this coil is in XY plane. So the direction of magnetic field will always be along the Z axis. When you will apply the modified right hand thumb rule, you will get direction inwards. Inwards means negative K cap and plus B2 for this coil 2. Now this coil 2 is in YZ plane. You will apply first the formula for the magnitude. So you will apply mu naught and the current in this coil is I2. Mu naught I2 divided by 2R. And can anyone tell me the direction? Means positive x-axis or negative axis? I have already told you the direction. The direction of magnetic field at this center point due to this coil, second coil, which is in YZ plane, will be along x-axis. Positive or negative? Uh, Nawal, can you tell me? You can apply your modified right hand thumb rule and you can decide the positive x-axis or z. And I have told you this direction is positive z x-axis and this direction is negative x-axis. Okay, just try to hold
Positive,
this
sir.
positive x-axis. Yeah, you are right. How you will get how you will find the direction? You will hold this coil like this. Okay, you will hold the coil. See this coil. Try this by yourself. Hold this coil uh, along the sense of the current. Okay, like this. The current is like this, and you should hold the coil like this. And your thumb will be uh, pointing towards right, pointing towards right direction. So means your the direction of magnetic field will be along positive x-axis, and for the positive x-axis, which unit vector we will multiply here? I cap. Now finish this question. Finished. The rest part is the calculation. You can take common mu naught divided by 2r. Mu naught divided by 2r is common. And here you can write I2 minus I1 k cap. So not the k cap. Mu naught divided by 2r is common. So this will be minus of I1 into k cap, and this will be mu naught upon 2 r is common. So here will be I2 into I cap. So I2 into I cap. So this is your final answer in the vector form. You can write the final answer. If the coil is in x, just note it down now. If the coil is in xy plane, and if anyone is asking you what will be the direction of magnetic field at the center, so definitely the direction of magnetic field along z-axis, but positive or negative, this will be decided by the direction of the current. So after this, we will discuss the derivation of magnetic field. Please note it down.
Yes, sir. Finish.
Done, sir.
In electric fields, the direction is very simple. Means no requirement of any rule and all that. Means either it will be away from the positive charge. If the charge is positive, then it will be away from positive charge. If the charge is negative, then the direction of the electric field will be towards the charge. But here the direction of the magnetic field is bit complicated compared to the electric field. So accordingly, we should know the rules, right hand rule. Just copy this. And when completed, please tell me.
Yes, sir, completed.
Good. So this time, your one coil is in XY plane. Means, here are two coils which are in the different planes. In the previous question, both the coils both the coils were in uh, XY plane. Matthew,
Yes,
then
sir. Done.
then okay. So just I so now see this. Write the heading magnetic field. Why my cursor is not working? Just wait a minute. So write the heading magnetic field on the axis of current carrying coil. Magnetic field on the axis of current carrying coil. So this is a coil. This is a coil. Okay. And I am taking this as in this direction x-axis and in this direction y-axis. And this is your current carrying coil of radius r. This is the center of the coil, and at a distance x, and this distance is along the axis of the coil. Okay. So this is the case like this. Suppose you can suppose a coil is placed like this. Suppose a coil is placed like this, and you want to calculate the magnetic field. Suppose the coil is here, and you want to magnetic field here on the axis of this coil. So we will discuss this derivation. So here I will do this derivation with the help of Biot-Savart law, and we know that Biot-Savart law, with the help of Biot-Savart law, we can calculate the magnetic field of a small element of wire only. So we will take the small element of this coil, and after that we will integrate. Then we will get due to whole of this circular wire or coil, you can say, at this point. So I am taking this is the small, very small element dl. I am taking here. And if I want to find the direction of this dl, I know that dl vector. Okay, so the direction of dl vector will be direction of the current. So the current is going like this. So we will draw a tangent. So this will be the direction. Please focus. This derivation is very important also and confusing also. So your direction of current is like this in this direction. Direction of this dl vector is this. I have just taken a small element here, and direction of this dl is given by the direction of the current. So direction of current at this point will be tangential by drawing the tangent. Earlier also we have done this here. Here we have taken the small element, we have draw a tangent, draw the direction. So now what I will do, I will join this dl, this point and this point p. So I am joining this with this p, and this distance is r. I am supposing this distance, suppose this the distance between this dl and this point p is r, and suppose here is some point q. You can suppose here some point q is there. So now we want the magnetic field at this point. So what we will do, we will apply the Biot-Savart law. For the Biot-Savart law, we will apply. I am just writing in a vector form, just for a minute. Mu 0 divided by 4 pi into I dl vector cross r vector divided by r cube. Why I have written in a vector form? Because I want the direction at this point of magnetic field first. Because in this derivation, the to finding the direction is complicated for the student. Means applying the formula and integration is comparatively easy. So when you will use this formula for this element dl, and then you will find that this magnetic field, this small magnetic field, will be perpendicular to this dl vector. Okay, and this dv will be perpendicular to r vector. So for this r, we can make this, from this r we can make this r vector. Okay, and for this dl we can make the dl vector. So this is the dl and this is the r. So direction of the magnetic field will be perpendicular to dl vector, means perpendicular to this also and perpendicular to this also. Okay, so the direction of magnetic field will be like this. This will be perpendicular to this, like this. So this will be your dv. This will be your dv. So how I have find it this dv, because this dv will be perpendicular to this r, for by using this. Now other things are simple. You can just open this formula or just write the scalar form of Biot-Savart law. So magnetic field at point P, magnetic field at point P due to current element PL. So dV will be the magnetic field at point P. This is equal to mu naught divided by 4 pi IDL sin theta divided by R square. So just write all these terms here. I have written all these terms. R is the radius of this coil, this capital R, and X, this is X is the separation between the center of the coil and this point P here. Okay, here is some point P, and N is the number of turns, okay, in the coil, and I is the current in each turn. So we are just calculating for one turn of the coil. Okay, uh, so these are the things. So what about this theta? So theta is the angle between the this r vector and dl vector. Theta is the angle between the r vector and dl vector. Already defined angle between dl vector and r vector. So this is the direction of the dl vector and this is the direction of the r vector. The point here is a very important point. The angle between this dl vector and r vector will be 90 degrees. Remember this point. This will be 90 degrees. Okay. This angle. This angle will be 90 degree. Okay. So put here theta is equal to 90 degree. So sin 90 is equal to 1. You will get, so magnetic field, small magnetic field at point P, you will get mu naught divided by 4 pi I into dl, because sin theta is 1 divided by r square. So this is the small magnetic field you will. But what will happen here now? Diametrically opposite element means there will be an element which will be diametrically opposite to this. Here, some here. Same small element dl will be here. And due to this same element, there will be the magnetic field. Okay, there will be the magnetic field at this point P, and this magnetic field will also be like this. It's from the symmetry. This time you can get, due to this element dl, there will be a magnetic field at this point P, and this dl will also be again at a distance of r due to the symmetry. Well, this is a symmetrical figure. And again the magnetic field will be perpendicular to this r. Magnetic field will be perpendicular to this r. So here you can write it like this. It will be like, it will be perpendicular this. This magnetic field dV will be perpendicular. So what is happening here actually? Here is one element. Due to this element, the magnetic field is dV in this direction, and there is another diametrically opposite element of this wire, due to which there will be a magnetic field also, and which that will be in this direction. So here we will use the components of vector. So this dV is vector, this dV is vector. So what I will do here, this is vector and this is. So as I have told you, I have already decided the x-axis and y-axis. So this is the x-axis. Axis of the coil is x-axis and perpendicular to this axis is y-axis. So what you will do, you will just uh, suppose this dV is making an angle theta. So this dV will also will make an angle theta. Okay. Don't take this angle theta because we have okay. Take this angle theta. Or we can take any angle. Suppose this angle is phi. So this angle will also be phi. Because theta we have already taken here. That is why I am not taking. So now you will take the x component of this dV and y component of this dV. So the x component of this dV will be like this: dV cos theta, and y component will be dV sin theta. And for this magnetic field, same thing you will do. So again, you will get for this magnetic field in this direction, you will get the dV cos theta as the component of this dV. And in this direction, I will get dV sin theta. I am using the components of the vector. So now you can see this dV sin theta and this dV sin theta will be cancelled out because these are equal and opposite vectors. Okay, and the remaining will be here will be dV cos theta. Okay, 2 dV cos theta. Uh, so no need to write this dV cos theta because just we want to know uh, due to this element, what will be the what will be the net magnetic field at this point P. Okay, this point. So this dV sin theta will be cancelled out. So here only be dV cos theta. So now uh, so dV is this, and this is the dV now. So what you will do, first you will take the magnetic field in x direction, then you will take the magnetic field in y direction and add those magnetic field vectorically. So in x direction you can write just a minute. So in x direction, the magnetic field will be dV cos theta. Okay. And in y direction, due to this component will be 0 because of this diametrically opposite component, both the magnetic field will be cancelled out. So the only magnetic field here due to this element will be dV cos theta only. So in x direction, dV cos theta; in y direction due to PL magnetic field cancel out due to diametrically opposite diametrically opposite identical element. So the net magnetic field at point P will be dB cos theta. So what is the value of dB? Now put the value of dB here. This is the value of dB. So this is dB and cos theta. Now, can we find cos theta? This angle is phi. Okay, this angle is phi, and this whole angle will be 180 degree. This whole angle will be 180 degree. So when you will find, you will get this angle as 90 minus phi. When you will apply this like this, see here, we'll do like this. This is phi plus this is phi angle. This is 90 degree angle, and plus suppose this angle this angle you don't know. Okay, so you have suppose this angle as x. This is 180. You will get this x is 90 minus phi. So that is why I have written. So you can write this as sine 90 minus phi will be xyr. Sine 90 minus, sorry, ry small r, because just 1 minute. You will write here sine 90 minus phi, and you are taking this triangle. You are taking this triangle. This point is POQ. Okay. This point is POQ. So you are taking this triangle POQ. So triangle PO. So this will become, what is sine theta? Sine of any angle equal to perpendicular divided by hypotenuse. So this is a right angle triangle. Okay. So you will take this perpendicular R, and this is R. Okay. Capital R by small r. This is capital R by small r. And sine 90 minus phi will be cos phi. 10th class trigonometry. R by R. So your magnetic field at point P will be mu naught divided by 4 pi. This will be I into dl divided by r square. So instead of this cos theta, I will put capital R by small r. Capital R by small r. Now at point P, the magnetic field mu naught divided by 4 pi into I dl into capital R and divided by small r. So this is the magnetic field at point P due to this current element dl. So for finding the total magnetic field, what you will do? You will integrate this equation. You will integrate this equation. Earlier also we have done the integration. So just integrate this on both sides. So when you will integrate this, so you will get the total magnetic field at point P, and you can take common from the integration, the constant term. This mu naught divided by 4 pi is constant, and this current is constant, this R is constant, and this thing is also constant. So you will take mu naught divided by 4 pi and I into R divided by R cube. This will be into dl. So Nawal, Matthew, and Nafisa, just tell me, are you getting something in this derivation?
Yes, sir. Telling you.
Because in this derivation, 80% or 90% is maths and 10% is physics. So maybe you are not getting properly, but when you will do the practice, you will get it properly. Because this in this derivation there are n number of things you have to remember. So the practice you can. So now, because each and every I have told you each and everything in this derivation. Okay. So now magnetic field at point P will be mu 0 divided by 4 pi into I into capital R divided by R cube. Now this DL will be the length of the wire. Length of the wire, total length of the wire. And what is the total length of the wire? 2 pi R. Okay. 2 pi into R. So here you will multiply instead of this DL 2 pi into R. Okay. And there is one more thing here. This small r. Now you have to go to this triangle again. Triangle POQ. Now from this triangle PO and this Q, so this angle is your 90-degree. So this will be your hypotenuse. So according to the Pythagoras theorem, this r small r can be written as this r square plus x square. So r square can be written as this square plus x square. So the r you can write root of r square plus. Now put the value of r here. This is small r here. You will get your answer. Magnetic field at point P is equal to mu 0 divided by 4 pi, and this will become IR square, and IR square into 2 pi. And instead of this, when you will do the cube of this r cube, okay. So here this can be written as x r square plus x square to the power 1 by 2. When you will do r cube, you will get this r square plus x square to the power 3 by 2. And now from here 2 pi and 4 pi, 2 pi and 4 pi can be cancelled out. Can cancel this 2 pi with this 4 pi. Here you will get 2. So finally the magnetic field at point P will be mu 0 or mu naught I r square divided by 2 times of r square plus x square to the power 3 by 2. So this is your final answer. This is your final answer for the one coil, means for the one turn. There are a lot of things in this derivation. We have done the integration, we have used the trigonometry, we have used the geometry, we have used the right hand side rule, we have used the Biot-Savart law, we have used the vectors also. So just please note it down. The heading is magnetic field on the axis of current carrying coil. So, Nafisa, have you got it?
Yes, sir.
Means Nawal
Yes, sir.
and Matthew.
Yes, sir.
So just now, please note it down. Okay, and please ask him to scroll down when finished. Just write these terms, all I have defined here.
So what's the second term?
This x, this is the
Oh,
x.
that's x. Okay.
Not looking like x, but this is x.
Yeah. So that's why I asked.
I make x, small x, not the capital X. This is small x. I make x like this. So this is small x. Don't think this is n or something else. This is small x.
So can you scroll down?
Okay. And now make this diagram. I'm zooming it. This is DL. Okay. DL means a small element of this coil. And this DV means small magnetic field due to this DL.
So can you scroll down?
So, Nawal and Nafisa, should I scroll down? Have you completed?
No, sir.
Not completed, na?
Yes, sir.
Means Nawal has completed. Nafisa, have you completed?
Yes, sir.
This derivation is already appeared in your CBSC exam. The thing that I am telling you, the thing which is confusing for the student, and that thing is the favorite for the exam. To ask in the exam. So remember this thing. After this, we will discuss the Ampere's law.
So can you scroll down?
Yes, sir.
So all of you, this is the integration, and I have done the integration. I think now you would have understood that in the earlier cases also I have done the integration. Why we do the integration? When we want to add small things, and those small things are very large. Means suppose I am giving you just I am giving you a room which is full of let's say this pen. A room which is full of this pen. Not a room, a building which is full of this pen. So what you will do? You will just I will say I want the total addition of this pen. So in that case, if you are sensible person, if you are just a person of human, then what you will do? You will not count this by yourself. Okay? You will try to find some technique. Okay. So in the same way, here is the technique integration. Integration is used for calculating small things, and those small things are very large. Means dl for dl with respect to dl, there is the magnetic field, and there are infinite number of dl, so we cannot add those magnetic fields manually. We will use some tool, mathematical tool or integration. That is why means integration is very important for physics. Means those who are maths students are aware of integration properly.
Sir, can you scroll up a little bit?
Fine. Now it's fine.
Yes, sir. No, no, sir. You can scroll down a little bit. Just yeah, it's okay, sir.
You have to practice this derivation at least 2 or 3 times.
Sir, can you scroll down?
Uh, Matthew and Nawal, should I scroll down?
Yeah.
Oh, I think this is the final. So B suffix P is the magnetic field at point P. And after this derivation, we will take a break of 5 minutes. Okay, then we will continue our class because we will have a class today, uh, 2 hour class. So you can take break of 5 minutes.
Yes, sir. Finish.
And after all of you, you can take a break of 5 minutes because I know that continuously you cannot tolerate. So take the break of 5 minutes. Then after 5 minutes, I will start. Okay, only 5 minutes. Just I will start up. Please don't leave the meeting. Okay, so now should I start now? Matthew, Nawal, and Nafisa.
Yes, sir.
Yes, sir.
So now just start. So we will start this Ampere's law. So in Ampere's circuital law, you can see here what is the Ampere's circuital law. This is the statement: line integral of magnetic field along a closed path is mu naught times the total current passing through the wire enclosed by the loop. So the meaning of this means, suppose you have this wire, you have this wire. So due to this wire, there will be some magnetic field. There will be some magnetic field on this due to this wire. We have already discussed. So for defining the Ampere circuital law, you have to just define a loop, Ampere's loop. Okay, Amperian loop. So if you have a straight wire, na, if you have a straight wire, what you should do? You should consider a Amperian loop. Suppose this is the straight wire carrying current in the upward direction. So you have to consider the circular Amperian loop. Circular Amperian loop you will consider, and uh, what you will do then? And now, suppose I am taking a point on this loop, but you should understand what is happening here. This is your wire, and around this wire there is a circular loop, and this loop is known as Ampere's loop or Amperian loop. So at this point, when you will find the direction of the magnetic field, you will apply the right hand thumb rule. Right hand thumb rule. So you will get the direction in the inward direction. You will get the magnetic field at this point in inward direction. In along this direction you will get. The magnetic field will be along in this direction, like this. Feel the direction of the magnetic field will not looking. So the direction of the magnetic field will be like this. Will be tangent. Okay, inward. Okay, and here when you will take dl, small length of this loop. Okay, when you will take the small length of this loop, suppose this is the dl you are taking here, dl vector. So the direction of dl vector will also be along this, because direction of the dl vector is along the tangent to the circle. Okay, so the direction of magnetic field is this and direction of dl is this. So Ampere says that if you do this, means line integral of, if you will integrate v dot dl, okay, then you will get the mu naught into the current in the wire, mu naught into the current in the wire. This is the Ampere's law basically. This direction actually will be not inward direction. This will be along the y-axis, because this is the z plane. Okay, so just write this down and write this statement of Ampere's circuital law. Then we will discuss it further. And this law is very simple. Means the calculation of magnetic field with the help of this law will become simple. And this is closed surface, so you can write this also. Just copy this. Remove this because this is a line integral, okay, and that sign is used for the surface integral. B here is the magnetic field at this point due to this current carrying wire, okay, and dl is the small length of this loop, Amperian loop, okay, this is Amperian loop. Written all of you, Nawal and Matthew and Nafisa?
Yes, sir.
Yes,
Yes,
sir.
sir.
So don't think this is complicated, just and there is a direction of the loop that we will use. So direction of the loop just means this is the Amperian loop, na circular Amperian loop you have taken for the straight wire. Now direction of the loop you can find with the help of right hand thumb rule. So just point your thumb in the direction of the current and curl like this. Okay, so direction of the loop will be this direction. This is the direction of the loop. Means anti-clockwise. Okay, this is the direction of the loop. So for the direction of the loop, so why I am writing all these things, you will get to know when you will solve the question. Direction of loop given by right hand thumb rule. Given by right hand thumb rule. This is very small topic. Ampere's law means we will have just here a derivation of straight wire, cylindrical wire, and we have solenoid. So just note this down. So now we will have the question. Just note this down. Direction of the loop given by the right hand thumb rule. From this question, suppose here is a loop. Loop means a closed something which is closed, like circle is a closed surface, but not the surface. Closed loop means you can see this. Suppose I am having a wire here, and suppose I am just doing this. So this become the closed loop. Okay. So here is a closed loop is here, and here is current. Okay. Here is the current. So this I3 represents the current is coming outwards. Current is coming outwards, and this cross I1 represents the current coming into the screen. Okay, and this I4 represents current is outward. I have already discussed, and you have to calculate the line integral of magnetic field. Line integral of magnetic field is given by this now. This is the line integral of magnetic field. V dot dl is the line integral of magnetic field. V dot dl is equal to line integral of magnetic field. Line integral or line integration of magnetic field. And what is this equal? This is equal to mu naught into the current enclosed in the Amperian loop. What is the current enclosed in the Amperian loop? This I1, I2 and I3, and we will take the current with sign. You can choose outward direction as positive direction. Okay, you can choose outward direction as the positive direction. So Matthew, please tell me what will be the expression of the current. I should write here. Means you have to choose the direction of the current.
I1 is inward, so
You will take
according
it
to
negative. You will take it negative.
yeah, negative.
So you can write minus I1 and plus I2 and plus I3.
Plus I3.
and you will not take this I4 because you
Yeah,
will
because
only
it's not in
take,
the loop.
yeah, because this I4 is not in the Amperian loop. So this is the benefit of this Ampere's law. Okay, and this question is all from your previous year exam. So, so this is over now. So now this is the Ampere circuital law, and don't confuse in this. Ampere circuital law is the line integral of magnetic field. What is the this is the Ampere circuital law. Okay. This is the line integral of magnetic field. Magnetic field dot dl is the line, and this integration is the this is known as the line integral of magnetic field. Actually, this is beyond your syllabus. Means this thing I think is beyond your syllabus means the small part of it is in your syllabus, but after 12th class, this is the part. Okay, so here is only the introduction of this magnetic. You have the simple integration in 12th class. So we have done this question also. So line integral we have just calculated now, and uh, so now if you have a straight wire, you have chosen a loop, circular Amperian loop. Okay. Now there are some criteria to choose the loop. Okay, so criteria to choose Amperian loop. Okay. So the Amperian loop you can choose can be the square loop, can be the circular loop. In 90% cases, we will take the square loop. Okay, for straight and so just write all these things. First point is we use Amperian loop to simplify B dot dl. Just wait a minute, my friend. Sorry for the note it down. Here we use Amperian loop to simplify B dot dl. B dot dl means line. This is line integral of magnetic field. To simplify, we use Amperian loop, and the Amperian loop should be closed like circle, like square, like rectangle. Okay, magnetic field should be uniform throughout the loop. Okay, when you are choosing a loop, make sure that the magnetic field is uniform throughout the loop, and a magnetic field should be tangential or perpendicular to the loop. So you can see this thing here. All these things you can find here. Uh, so this magnetic field is tangential to the loop. Okay, this is the loop, circular loop, and this magnetic field is tangential. Okay, and at any point on the loop, the magnetic field will remain same. If you will find the magnetic field here, here also the direction of magnetic field will be like this, and the magnitude also the of magnetic field will be same. Okay, at all the points of the loop, the magnetic field will be same, and this magnetic loop is closed also. So there are the few points that you have to. And for straight and the cylindrical conductor, Amperian loop is circular. So we have earlier a straight conductor. So we have choose the circular Amperian. So write this down. These steps. I am taking a 2 hour class because we are having only 2 classes in a week. And if I will not do so, we will not reach to the syllabus. Just write this these points. dl is the small element of the loop. When completed, just please tell me. This is the sign of perpendicular. Perpendicular.
Done, sir.
Nafisa, done.
Yes, sir.
Now, proof of Ampere circuital law. Proof of Ampere circuital law. This can examiner can ask you proof Ampere circuital law. So what is the meaning of that? This is your Ampere circuital law. Means you have to prove B dot dl is equal to mu naught into I. So for that, what you should do, you will have you have to suppose there is a conducting wire, and in this wire the current is in this direction, and you will find the direction of this loop. The direction of the loop will be this. You will apply the right hand thumb rule. Curl your finger, means your thumb should be in the direction of the current, and curl your fingers. So the movement of your finger will be the direction of the loop, ampere loop. So here you have the straight wire you have taken. So you will choose the circular loop. You will choose the circular loop, and this is closed also. So okay. So this is the ampere loop. And when you will find the magnetic field at any of the point, so you are already know this circular thing is a Amperian loop, so no need to write it. So just you can take this point. Suppose at this point you want to find the magnetic field due to this current carrying wire. Okay, so the magnetic field will be like this, and the direction of the magnetic field will be tangent to this circle, and the direction of dl, if you will take the small length of this loop dl, direction of dl vector will also be along the tangent. So mean direction of b and dl will be same. Direction of b and dl will be same, and also this magnetic field is constant. Suppose now you are finding the magnetic field at this point. So here will be the direction of the magnetic field. This is the positive, this is along the positive y-axis. So like this, you can write this is the direction of the magnetic field, and direction of the dl also will be same. This here. So here the magnetic field B is uniform or constant. Constant means at every point of the loop, at each point of loop, here if you will find, you will get the same magnetic field, means the magnitude you will get same. So you have to find this b dot dl. Now open this b dot dl. This will become b into dl into cos theta. And what will be the theta? Theta will be the angle between the b vector and the dl vector. So the angle between the V vector and the DL vector will be 0 degree. Okay. So when you will put cos 0 here, cos 0 is 1, 0 degree is 1. So you will get this V into DL, and integral will also there, V into DL. And I have told you V is constant. So you can take this V out of the integration. Now you have this DL. And what is DL? DL will be the length of the circle. What is the length of the circle? 2 pi into small r. Okay. You can write this V into 2 pi into small r. Okay. And one thing more. As this is the long wire I have supposed. Okay. If nothing mentioned, you will suppose the wire is long. Long wire means infinitely long wire. So what will be the magnetic field at a distance r? What will be the magnetic field at a distance r due to long wire? This B, value of this B. We already know this magnetic field due to the, this will be mu naught divided by 4 pi 2 I by r. This B will be mu naught divided by 4 pi 2 I divided by r, and this is into 2 pi r. So magnetic field due to long wire. Wire V is equal to mu naught divided by 4 pi 2 I divided by r. This formula I have used. So now this r and r will be cancel out. This 2 pi and this here will be 2, and this cancel out. So finally you will get V dot dl. You will get mu 0 into pi. So finally now you have proved this. This is the proof. So in this way you will prove this. Just copy this. First you will consider a straight wire, and then you will consider a circular loop. Then you will calculate V dot dl. Okay. And the value of magnetic field we already know due to the long wire. Please note it down.
Sir, please scroll down.
Nafisa, scroll down.
Yes, sir. Scroll down. Yes.
So in this way you can prove this formula. Already I have discussed magnetic field due to a long wire or infinitely long wire at a distance r from the wire. So please note it down. We have 3 more minutes.
Done, sir.
Nafisa, completed.
Yes, sir. Finish.
Nawal. Okay. This is done, na? Now there are the application of Ampere circuital law. Okay. So there are the application of Ampere circuital law. So in the application part, we will discuss, we will apply the Ampere circuital law to find the uh, magnetic field. Okay. Suppose this is the first point, means the first application. We will find the magnetic field outside and inside of the current carrying cylindrical wire. So, so you suppose you have a cylindrical wire. This is a cylindrical wire of radius capital R, and in this cylindrical wire, the current I is flowing. Current I is flowing. Suppose you want to find the magnetic field at this point P. So what you will do, you have a cylindrical wire. Earlier I have discussed, if you have a cylindrical wire or a here cylindrical wire. So what you will do, you will choose for straight and cylindrical wire, Amperian loop is circular. So you will choose an Amperian loop. Here you will choose an Amperian loop will be circular. So same thing you will do. Here the magnetic field will be V vector, and small length of this loop dl you will take, and again you will calculate B dot dl is equal to mu naught divided by 4 pi r. So first step for this, consider a circular Amperian loop of radius r greater than a. So here you will consider a loop, okay, which is whose radius should be greater than a, because we want to find the magnetic field outside. That is why we are taking a loop which is greater in size with respect to this cylinder. So what now we have this Ampere circuital law. B dot dl is equal to mu naught into current inside. Now we will calculate B dot dl. So how we will calculate B dot dl? B dot dl. So we will write here P into dl into cos theta. See here, theta, both the direction are same. Direction of B and dl are same, so theta will become 0 degree. So here B will be out of the integration. Here is dl. So dl will be the length of this loop. So length of this loop will be 2 pi into small r. 2 pi into small r. So your B dot dl will be 2 pi r. Your B dot dl vector is equal to 2 pi r, and this is your equation number 1. Now you have to find what is the current inside. Current inside will be I. You can see here current inside will be I only. So now you will put all these value in this formula. You will apply now the Ampere's law, and okay, this is B dot dl is equal to mu naught into I in. So B dot dl you have 2 pi into small r. B dot dl is equal to 2 pi into small r, and this is equal to mu 0, and I in means I we will write here, and this is B into 2l. Here is now, here you should write this, not 2 pi r, B into 2 pi r you will write, because this B will also be included here. So B into 2 pi r, this will be B into 2 pi r. This is equation number 1. So from here you can find magnetic field. Okay, so this will become mu naught I divided by 2 pi into r. So this is your final magnetic field with the help of Ampere's law. This is your magnetic field. Amperes per meter. Means here we have applied, and earlier also I have find this magnetic field, but you can see here earlier also we have find the magnetic field due to infinitely long wire. So when you will solve this, you will get the same answer. P is equal to this 2 and this cancel out. So mu naught I divided by 2 pi r you will get. So see, with the help of Ampere's law, these things will the things will become easy. Just note it down. Just copy this, and we will discuss the next thing in the next class. I think that's enough. Please note it down, and rest of the things we will discuss in the next class. I have chosen here a circular loop because this wire is a cylindrical and straight. Okay, this wire is cylindrical and straight, and at this point, the direction of the magnetic field, when you will apply the right hand thumb rule, will be tangential to this means loop. Okay, that is why I have taken the direction here in this direction, and direction of DL will always be tangential to the circle or the loop you have. So the
So can
direction
you scroll down?
scroll down.
Yes.
Just copy this, and the rest of the things we will discuss in the next class. This is 2 pi into r. And I will share with you the notes of the current electricity. Okay. So I will share on the group now. You can get from the group.
Okay, sir. Yeah.
Sir, I'm not in the group.
You are not in the group. Okay, no problem. I will tell to the team. I will
Okay,
let
sir.
you. I will share whole of the slides of the current electricity. I think that will be helpful for you. This part is very large, means that the part of electromagnetism. Electromagnetism means electrostatics, current electricity, and this magnetism means magnetism and EMI and AC. When this is completed, means you can say 70% syllabus is complete. Earlier you have
Sir, scroll down.
after that you have optics and modern physics. That will not take much time.
Done, sir.
Then Nafisa,
Yes, sir.
so, mm, so we will meet in the next class, and please before coming to the class, please revise your notes. Okay, and